Electrochemical cells. In order to understand the electrochemical cells, consider a reaction between zinc and copper sulfate. When zinc powder is added in copper sulfate solution, then the blue color of copper sulfate solution vanishes and copper metal settles down. So let's see the actual redox reaction which is taking place in this complete reaction, in which zinc metal having oxidation state 0 and the copper having oxidation +2. So here copper is copper ion. Zinc metal have been converted to zinc ion, whereas copper ion is converted to copper metal having oxidation state of 0. So in this redox reaction, let's see, there are two half reactions. The first one is the oxidation half reaction, in which zinc metal have been oxidized to zinc ion with loss of 2 electrons, whereas copper ions have been reduced by gain of 2 electrons. So the overall this complete redox reaction is sum of these two reactions. So now let's discuss how we can make an electrochemical cell. For this purpose, arrange two solutions. Here we have the diagram. So arrange two solutions by adding zinc rod in zinc sulfate solution and copper rod in copper sulfate solution, and join the two rods with an external circuit having a voltmeter, and then connect these two solutions with a salt bridge. This salt bridge contains a salt which allow only the movement of the ionic species across this bridge. The oxidation half reaction is taking place in the left beaker, whereas the reduction half reaction is taking place in the right beaker. In these half reactions, the electrons are being given by the zinc metal into the external circuit, and these electrons travel through the external circuit and then they come to the copper, and then they are taken by the copper rod, at which the copper 2+ ions are reduced, and in the left hand chamber zinc ions are produced from the surface of this zinc rod as the zinc metal is giving electrons to the outer circuit, whereas the copper ions present in the copper sulfate solution are gaining electron at the surface of this electrode and converting to copper metal. So what's the role of salt bridge here? Salt bridge is actually a U-shaped tube containing a concentrated solution of a strong electrolyte like potassium chloride or potassium sulfate. This bridge makes the contact between the two solutions for the movement of ions without mixing these solutions. Using this arrangement of the electrochemical cells, the electrons are moving through the external circuit, whereas the ions are moving through this salt bridge. And here we can see that the number of zinc 2+ ions are increasing, and in order to balance the counter charges, the sulfate ions will move through this salt bridge and then bring about the electrical neutrality. And for the right hand reaction, as the number of positive charges are changes to metal, with zero oxidation state. So here the number of positive charges are decreasing, and in order to balance the electrical neutrality, the potassium ions from the this salt bridge will move towards this right hand chamber. So in this way the electrons move in the outer circuit, whereas the ions or ionic species move in this inner salt bridge. And overall the conventional current have direction towards opposite to the flow of electrons. And in this discussion there are some important points which must be understood to fully comprehend the electrochemical cell. So first one is the oxidation is taking place at the zinc electrode, and it is called the anode, whereas reduction takes place at the copper electrode, and it is called the cathode. Second point is for zinc rod, that is rich in electrons because the zinc metal is undergoing through our oxidation process in which electrons are produced that are entered to the external circuit. So this electrode is called the negative pole. The copper electrode is poor in a number of electrons because the electrons have been utilized for the reduction of copper 2 plus ion to copper metal. So this electrode is known as negative pole. The zinc electrode releases the zinc ions and the electrons are set free, and the zinc ions become excess in the left beaker, and the sulfate ions from the salt bridge compensate these excess zinc 2 plus ions to make the solution neutral. Whereas when the copper 2 plus ions are reduced to deposit in a form of copper metal at the surface of electrode, the number of positive charges are decreasing. So in order to balance this positive charge that is lowered is being balanced by the potassium ions that are coming from the salt bridge to make this solution neutral. And this in this electrochemical cell, the net result is the weight of copper electrode that is increases, and the weight of zinc electrode that is decreases. And the tendency of the net flow of electrons through the outer circuit decreases due to the changing the concentration of the zinc and copper ions in both beakers. Now let's check out another example in which now copper electrode have been used as the anode, whereas silver electrode or silver wire have been used as cathode. And in the left hand direction, copper electrode or the copper metal rod is in contact with its solution, that is copper nitrate solution, whereas in the case of the right hand direction, the silver electrode or silver rod or silver wire have been in contact with the its solution, that is silver nitrate solution. In this kind of cell, copper is being oxidized whereas silver is reduced. That is in contrast to the previous cell in which copper was reduced. It means that the relative tendency of one of the electrode as compared to the other, whether it will lose electrons or gain electrons, depend on the energy levels of these metal electrodes, for example. Now consider the energy levels of the zinc and copper metals, in which this empty space is known as valence band, and this filled space is known as conduction band. And this level where the probability of electron density is 50%, this level is known as Fermi level. And the relative tendency of the reduction or oxidation of species depend on this Fermi level. If the Fermi level is higher, then the electrons will jump to the lower energy level of the other species and reduced it. In two examples, in first electrochemical cell, the Fermi level of zinc metal is higher and the electrons tend to reduce the copper ions, whereas for the second case the Fermi level of copper ion is higher and it is reducing the silver ion. So in first electrochemical cell, the copper 2+ ions are being reduced, whereas here copper metal is being oxidized. So in this way we can have many combination of the electrochemical cells in which we have different kind of electrode systems. So the tendency of the reduction or oxidation will depend on the Fermi levels of these electrodes that are actually, this boundary is connected by the external circuit. So in this second electrochemical cells, copper is oxidized here to make this copper rod electron rich. So this is known as the negative pole, and electrons are being transported to external circuit, and here these electrons reduce the silver ions to silver metal, which is deposited over this electrode. And here with the deposition of this silver ions to silver metal, where the oxidation of silver is 0. So in this case the number of silver ions are decreasing in this chamber. So then in order to make this solution electrochemically neutral, the potassium ions move to this solution through the salt bridge in order to make the electrochemical neutrality, whereas for the case of left hand electrode, the number of copper +2 ions are being generated. It means the number of positive charges are increasing. So here the counter anions are being moved to this left hand solution to make the solution electrochemically neutral. So here we have seen that the copper electrode in this electrochemical cell is acting as anode, but in previous electrochemical cell it was acting as cathode. So it depends on the type of redox reaction, either it is oxidation or reduction, which one is taking place or over the electrode, then the electrode is termed as either anode or cathode depending on the type of redox reaction. Conventionally, the left hand electrode is usually chosen in a way to make it the anode, whereas the right hand electrode usually act as cathode. Now let's check out another assembly of the cell known as electrolytic cell. This is an arrangement given here in which the electrical energy is being supplied to bring about the electrochemical reaction, that is the redox reaction, and otherwise we can call it the non-spontaneous. The previous cell which was known as electrochemical cell was actually the galvanic cell, in which the process of conversion of electrochemical energy into electrical energy was spontaneous. So in the previous cells we have observed the spontaneous conversion of chemical energies to electrical energies, and we have a voltmeter which was used for the current generated in terms of the measurement of volt. Whereas the electrolytic cell is the non-spontaneous generator that actually converts the electrical energy into chemical energy. In this type of electrochemical cell, the electrical current is passed through the molten salt, for example molten sodium chloride. In this kind of cell, the sodium ions that is from the molten sodium chloride are being reduced to sodium metal, whereas at the surface of cathode the chloride ion from the sodium chloride molten salt that generate sodium and chloride ions. So these chloride ions are being oxidized at the surface of cathode. So in this arrangement, the external source of potential difference is applied to the electrodes, which bring about these two electrochemical reactions. The first one is the reduction of sodium ions at the surface of cathode, whereas the second one is the oxidation of chloride ion to chlorine gas at the surface of anode. So here we have overall that is the net reaction. So in this cell, the electrical energy have been converted to chemical energy. So in this lecture we have discussed about the two kind of electrochemical cells, in which first what was known as galvanic cell, in which the chemical energy was converted to electrical energy through spontaneous conversion of energy, whereas for the second case, that is known as electrolytic cell, we haven't used any salt bridge. Here the reduction is taking place at the anode, whereas for the case of galvanic cell the process of oxidation is being observed at the surface of anode, and conversely the oxidation is being observed at the cathode, but here the reduction is taking place at the cathode. Here the successful electrochemical reaction depend on the relative energy levels or Fermi levels of these two electrodes, but in this case we have a setup in which the amount of currents applied to the electrodes and thus to the electrochemical cells are directly relevant to the type of salt or electrolyte is being used and the relative energy levels of the electrodes and the electrolyte. Of electrolysis, Faraday discussed the quantitative relationship between the quantities of the substances that are deposited at the electrodes and the quantity of electricity passed. He has given two laws which are discussed as follows. So first law of electrolysis states that the mass of any substance deposited or liberated at any electrode is directly proportional to the quantity of electricity passed. For example, here we have a cell in which molten sodium chloride salt have been used, and that is connected with an external circuit upon which an external uh, electrical energy is being applied to the electrode, and thus the sodium and chloride species are reduced and oxidized to deposit sodium metal and liberate chloride ion at the anode and cathode surfaces. So here the weight or the amount of these species that are being deposited or liberated are directly proportional to the amount of electricity or the quantity of electricity passed. So let's W is the grams of substance that is deposited on passing Q coulombs of electricity, which are proportional to each other. By replacing the proportionality constant, we need Z, that is electrochemical equivalent of substance that is deposited. So here Z is the electrochemical equivalent of the substance deposited, and it depends upon the nature of the substance. So here in this first law we have expressed the electricity in terms of the charge that is given in coulombs. So the quantity of electricity in coulombs is the product of the current in amperes and time in seconds. So here we get two equations, so we can combine these two equations. So we get weight of the substance that is deposited or liberated at the surface of electrodes in terms of the electrochemical equivalent of the substance deposited into current and time in seconds. Conversely, we can say that the electrochemical equivalent of a substance is the mass of that substance deposited when a current of 1 ampere is passed for 1 second. So we can call this electrochemical equivalent of substance that is deposited is equal to its weight. So we can say that electrochemical equivalent is the mass of the substance deposited when 1 coulomb electricity is passed through the substance. So here the ratio ampere over second is equal to 1 coulomb. Now let's discuss about the different units that have been used in the first law of electrolysis given by Farady. So here coulomb is a unit of electricity, and 1 coulomb is actually equal to 1 ampere into 1 second. So here coulomb is a unit of electricity, and another unit of electricity is known as Faraday, which is a bigger unit of electricity, and 1 Faraday is equal to 96485 coulombs. And it has been found that when 1 Faraday of electricity is passed through the electrolyte solution, then 1 gram equivalent of the substance is deposited. So mass deposited by 1 Faraday is actually equal to the 1 gram equivalent, and mass deposited by 1 coulomb is actually equal to 1 gram equivalent over, so as 1 Faraday is equal to these number of coulombs, so we have to divide these number of coulombs to get 1 coulomb in terms of Faradays. So we have to divide with the number of Faraday units, 96485. So 1 gram over 96485 coulombs per mole is actually known as electrochemical equivalent. For example, when 1 Faraday of electricity is passed through silver nitrate solution, so we have passed 1 Faraday electricity, then 108 grams of silver is deposited. So how we can calculate the gram equivalent or the electrochemical equivalent of silver? So for this calculation we have to divide the gram equivalent that have been generated over the Faraday's unit 485, that must be equal to 0.001 nearly. Now let's discuss Faraday's second law of electrolysis. This law defined as when the same quantity of electricity is passed through the solutions of different electrolytes connected in series, then the weight of the substance produced at the electrodes are directly proportional to their equivalent weights. For example, if we have 3 connected electrolyte solutions that have been connected in series, so the amount of current is passed through each of the electrolyte solution is same. So the number of equivalent weights that are generated from the weight of the substances that are present in the solution are directly related. In order to understand it, pass the same quantity of electricity through copper sulfate and silver nitrate solution which are connected in series. So let's take only the 2 electrolytes that have been connected through a series connection, and when the same quantity of electricity is passed through the 2 solutions, the weight of copper deposited is equal to the equivalent weight of copper. That is for the case of when 1 Faraday of electricity is passed through these electrolytes, then the ratio of the weight of copper deposited over the weight of silver deposited will be equal to the equivalent weight of copper over equivalent weight of